Hi, and welcome to Developing for Intel Graphics Today and Into the Future. My name is Kyle Grawl, and I am a graphics software application engineer with Intel. I have been in this role for the past 4 years, working with game developers to ensure their games run well on Intel's hardware, both CPU and GPU. I have 10 years experience at Intel, previously working on physical design and layout of hardware. Today, I will be discussing best practices to ensure that games today can take advantage of currently enabled features on Intel graphics. I will also discuss how to ensure that games can take advantage of upcoming features when they become available. We will first discuss current Intel graphics and trends. Next, I will speak about general detection and features and extension support for DirectX 12 and Vulkan. After that, I will briefly explain how SIMD on Intel works. Finally, I will go over a list of features to prepare for. Intel has been increasing the graphics capabilities of our cards generation over generation. Starting with Gen 11, we've delivered an integrated graphics solution that could deliver up to 1 teraflop of performance. Compare the previous Gen 9 solution, we increased the core compute capability by 2.67 times at ISO frequency. With the introduction of XELP, that capability increased further. Along with these increases in compute power, we also support modern graphics APIs, such as DirectX 12 and Vulkan. We have also added support for various DirectX 12 and Vulkan features. Our next big leap in graphics is entering the discrete graphics space. We've started sampling with customers, and we can't wait for developers to get their hands on these soon. With all that being said, it's pretty obvious that GPU hardware is constantly changing with each generation to try to meet the needs and expectations of game developers. One generation of hardware may not support certain features in an API, but future generations may. With this in mind, it may be prudent to ensure that you are checking for features you need in your game with hardware non-specific extensions and APIs. To check for this, DirectX 12 and Vulkan offer APIs to query available hardware. For DirectX 12, check feature support along with checking for proper feature level can help with this. Vulkan has similar capabilities with VK physical device features and a list of extensions with VK enumerate instance extension properties. As stated before, future generation of hardware from a vendor may support new features that are not supported today. It is best to avoid using vendor IDs to disable features, using slower execution paths, or defaulting to low settings. Gone are the days of if Intel disabled part of your pipeline, low settings, etc. Always check to see if the hardware detected supports the features needed and meet the technical requirements for your game. Lastly, always keep in mind the different architectural differences between vendors when using features. One last thing to go over related to hardware detection is our driver versioning system update. There may be cases where you may need or have previously needed a specific driver version or greater from Intel to support your game. We now recommend checking all 7 digits for the build number. As you can see on the right, the build number is the last 7 digits of the driver version number. If you have older code that is checking the last 4 digits, please update your code to ensure your games will run on Intel. Without this, your game may incorrectly tell the user to update their driver, or even worse, prevent the game from starting or crashing. For more information, please check out the link listed here. This article goes into further detail explaining our driver versioning schema and can help you if you need to check for a specific driver version. Now that we've discussed how to ensure software today and in the future can check for feature support to be flexible for future hardware, I will discuss at a high level how SIMD works on Intel. On Intel graphics, execution units, or EUs, are the core of our execution of shader code. Physically, our EUs are SIMD8, but logically support up to 32 wide instructions. Depending on thread register usage, the compiler will choose which SIMD width to run. Higher than SIMD8 instructions pair adjacent registers. For instance, SIMD16 would pair 2 physical registers together. One way to ensure you get the best SIMD usage is to reduce register pressure and avoid fills and spills from memory, which can be costly and result in execution unit stalls. This will enable better latency hiding, better instruction pipelining, and better code generation. Here are a few tips to reduce register pressure, which may be a reminder for some of you. Try to avoid branching on constant buffer conditions and non-uniform access to buffer data. This can increase the number of registers used since each path will take up registers. The same applies for excessive variable declarations, including but not limited to arrays. When possible, use partial precision formats, move common code outside of branches, and use specialization contents to reduce register pressure. This can help the compiler achieve higher SIMD usage. Below is a good rule of thumb for understanding how register usage affects SIMD width. Each thread has up to 128 registers. Using more registers can lead to lower SIMD width. Even worse, excessive use can result in spills and fills from L3 cache or main memory, making latency hiding harder to accomplish. The rule of thumb for register usage per thread is 64 registers and below result in wider SIMD lengths, 64 to 128 result in SIMD 8, and lastly, going over 128 registers per thread can result in SIMD 8 with fills and spills into L3 cache or memory. This is the situation we want to avoid for performance. In summary, reducing register pressure helps ensure you get the best SIMD width for better latency hiding, better instruction pipelining, reduced fills and spills from memory, and better code generation. Since SIMD is dependent upon compiler choices, it is wise when developing not to make assumptions about SIMD lane counts. Use get wave size and similar wave intrinsics to get wave count. Swizzle operations on one hardware vendor may fail on another. Another important thing to note is race conditions can happen when SIMD is different than thread group size. This can lead to read after write hazards and lead to corruption if one thread group depends on the data from another thread group. To ensure you're getting correct read-write behavior, use barriers to enforce this behavior. On the other side, if a thread group does not depend on each other for data, avoid barrier use as they will introduce unnecessary waiting conditions. Next, I will be talking about features to plan for. First, we'll talk about adaptive sync. Adaptive sync has been supported since Gen 11, which is also known as isolate graphics. The aim of adaptive sync is to relieve screen tearing and stuttering on displays that support it. The diagram to the right shows typical conditions in games. When VSync is enabled, there may be screen lag between when the frame is rendered on the GPU and when it is displayed to your monitor. While this will result in no screen tearing, the cause is with the latency to the display. When vertical sync is turned off, the display can swap frames as soon as they become available. However, this may result in screen tearing. We've all seen cases where trees, buildings, etc. do not look right because of the display swap to presenting a new frame before the current frame finished rendering. With adaptive sync, this problem is alleviated on displays that support it. Along with having a display that supports adaptive sync, the user has to enable it in the Intel graphics control panel. As game developers, you can enable this feature as part of the swap chain creation process. For DirectX 12, there are two flags you need to set: swap chain allow tearing and present allow tearing. For Vulkan, VK present mode immediate and VK mode FIFO can be used in the swap chain creation process for Vulkan. High dynamic range support is another feature currently enabled on Gen 11 and beyond. High dynamic range support on displays allows for the use of wider color gamuts that result in higher visual fidelity. Games wishing to support HDR in DirectX 12 need to do the following. The swap chain must be of flip sequential or flip discard, and Microsoft recommends using the format RGB10A2 UNorm. Also, the color space must explicitly be set to RGB full G2084 none P2020. In addition to those requirements, DXGI Output Description 1 describes information about supported color spaces, color information, and luminance values that can be used to adjust tone mapping and post-processing. Next thing to point out is queue support on GPUs. GPUs can support multiple queues that have different functionality. At the top, you can see examples of different queue types. For instance, a universal queue may support graphics pipeline, a compute pipeline, copy and transfer operations, and present operations. Another queue may just support compute or compute along with a copy. There may be even the case of where a queue only supports copy operations. All of this can help enable asynchronous compute. For instance, while the graphics pipeline is running operations on the graphics queue, another queue can be dedicated to running a compute workload or be in charge of copy operations. This will require necessary synchronization to ensure resources are available if there are dependencies, but the end result is possible better utilization of the hardware. In DirectX 12, if the hardware has multi-queue support, creating a queue for compute and submitting compute command lists on that will enable async compute. On the right column on Vulkan, it's a bit more explicit. VK get physical device queue family properties can enumerate queue families and report out which kind of operations they support. You can then create the necessary queue on that family. Always check the limits on what the queues support. For compute-only work that would benefit from async compute, submit command lists to the non-graphics work queue. It is important to always profile to see if there is any benefit to doing this. One thing to avoid is overlapping compute work in both the graphics and command queues. This could result in reduced performance or no benefit at all. This advice applies to both DirectX and Vulkan. For upcoming products, we'll be offering ray tracing acceleration on specific hardware. Ray tracing allows for the use of ray operations to solve different rendering problems, such as ambient occlusion, global illumination, shadows, and so forth, rather than using existing compute-only or screen space solutions. Ray tracing starts with ray generation and traverses an acceleration structure to help with performance. Based on what is encountered, different shaders are ran and can either trace more rays or execute a miss or closest hit shader. Early guidance from Intel recommends using trace ray over inline ray queries, using index meshes for BVH builds, and batching acceleration structure build operations. When building acceleration structures, do not interleave barriers if it is not necessary, as this will introduce non-necessary waiting. Do them all in one command list and barrier at the end to signify that building is done and the acceleration structure is ready for use. Mesh shading is a new development that is in DirectX Ultimate. The aim of mesh shading is to replace the traditional graphics pipelines input assembly, vertex shader, hole shader, tessellation, domain shader, and geometry shader with a two-stage pipeline consisting of an amplification shader and a mesh shader, and output geometry in a compute shader fashion. Rasterization and later stages are still the same. With mesh shading, you can transform geometry, call primitives, generate geometry in small batches without fixed functions. Pre-calling the stage can reduce the amount of work done to the rasterizer and has the potential to reduce the number of pixel shader invocations, saving frame time. It is still recommended to pre-call, if possible, on the CPU with other known techniques, such as frustum calling, software mask occlusion calling, and so on. Any work that ultimately does not end up getting on the GPU and is discarded before it reaches there, because of clipping, culling, etc., will add efficiency to your graphics pipeline. By default, mesh shaders will run in SIMD8 or SIMD16. Be aware that hardware will allocate for the worst case scenario, and that big meshlets can lead to lower efficiency. The last feature we want to make you aware of is variable rate shading, also known as fragment shading in Vulkan. This feature allows developers to increase the visual quality while maintaining frame rate. If you have pixels that do not add to the visual fidelity, such as those on faraway objects, objects under motion, pixels in the peripheral, so on and so forth, those pixels can have reduced shading rates. Different hardware supports different shading rates. Among those are 1x1, 2x1, 2x2, and 4x2, and 4x4, and so on as seen in the figure on the top right. With this in mind, both DirectX 12 and Vulkan have support for this feature. On DirectX 12, there are two tiers of variable rate shading. Tier 1 allows controlling a shader rate on a per draw and per primitive basis. Tier 2 allows for controlling shading rate based upon a low resolution image, as can be seen on the lower right. The screen captured in the lower right demonstrates Tier 2 and image-based support. Pixels in red are at a shading rate of 1x1, which is the default shading rate when not using VRS. Green is a shading rate of 2x2, and blue on the outside is a rate of 4x4. In Vulkan, this is supported via the fragment shading rate extension. If the extension is available, you will need to check for feature support for per draw, per primitive, and image-based support, based upon the need of your game. VK physical device features can be used to probe for support. With this in mind, it may make sense to experiment with different shading rates, especially if you are pushing for higher resolutions, since this can reduce the pixel shading rate and thus the number of pixel shaders invoked. Always check to see if the visual quality meets your expectations and aesthetics that you're aiming for in your game. We've covered a lot of ground in this talk. The capabilities of Intel graphics are ever changing in both compute and features. With this in mind, To ensure your game today will be able to take advantage of future hardware, it is best to use good GPU detection code to help guide enabling of features for Intel. Avoid disabling features based on vendor ID, ensuring that future graphics products from Intel can use these features. As mentioned earlier, gone are the days of if Intel disable parts of your pipeline. Also, be aware of our new guidance regarding checking graphics driver version. Use the last 7 digits of the driver version to get the full build number and check against that. If DirectX and Vulkan support a feature, it is best to use the DirectX 12 and Vulkan non-vendor specific APIs and extensions for adaptive sync, HDR, ray tracing, mesh shading, and variable rate shading. The other thing to remember when developing for Intel is our variable SIMD size. Do not make assumptions about wave size, as this can lead to unexpected behavior between different hardware vendors. Also keep in mind to design your shader algorithms to work with any SIMD width. The other thing to keep in mind when using Vulkan extensions is to check for supported sizes and limits. Different vendors specify different limits in their driver based on the driver and hardware capabilities. If you're using middleware, make sure your middleware is using the right features as well as checking for proper support. Finally, GPUs can offer multiple queues that have the potential to increase the performance of your game. Check for queue support and plan your work submission pipeline accordingly. Always profile your code to see if your game benefits from async compute. Thank you for joining us today. It has been an honor to be here and to get you ready for the future of Intel graphics. At this time, I will open it up for Q&A.